afternoon, everybody. So, good morning for some ones, good night for others. So, thank you very much for joining for this new CASS talk that is organized by IEEE Sequencing Systems Society Rio Grande do Sul chapter, together with Federal University of Rio Grande do Sul. So today we have the pleasure to have here Professor Alberto Sangiovanni-Vincentelli. So if you try to read his achievements in all his career, we would have to do another talk about. So here, just some brief highlights. So Alberto Sangiovanni-Vincentelli is the Edgar L. and Harold Butner Chair of Electrical Engineering and Computer Science, University of California, Berkeley. He has been with Berkeley since '75. Special advisor to the Dean of Engineering for Entrepreneurship and chair of the faculty advisors to the Berkeley Accelerator, SkyDeck. Many awards. So some of them is the prestigious Kaufman for pioneering contributions to EDA, IEEE RSE Maxwell Medal for groundbreaking contributions that have had an exceptional impact on the development of electronic and electrical engineering or related fields. In industry, he is co-founder of Cadence and Synopsys, the two leading EDA companies with combined evaluation in NASDAQ of close to $60 billion US. Member of the board of directors of Cadence, KPIT, ISEO, Expert System, Ultra SOC, where he's chairman, Cogigen, consultant for companies worldwide, including Intel, IBM, ST, Mercedes, BMW, UTC, General Motors. He's chairman of International Advisor Council. He's in Milan Innovation District area. Member of NAE, IEEE SCM Fellow, honorary doctorate from Aalborg University and from KTH in Sweden. He has published more than 1,120 papers and 19 books with age index of 115, and he has already graduated over 100 doctorate students. So it's an impressive short CV, no? And for us, it's a great honor to have today here a talk by Alberto Sangiovanni-Vincentelli. So I will give you back the control of the slides. Then you can do your screen sharing to start your talk. Thank you very much for accepting our invitation.
Thank you, Ricardo, for allowing me to present my work to your chapter. And my presentation today is about a bit of a history of my life and what I've done over the years, and a bit of projection of what is going to be the future. So it is a mixed talk. So it's not really a technical talk. It's about the history of EDA and what has happened in the past few years. So the outline of my talk is that I'll start with the history of EDA, and then I'm talking about what the future is going to be. So how we extend EDA from electronics to other fields. And so we are going to touch upon cyber and bio-cyber-physical system, then the relationship with artificial intelligence, and then I will briefly mention a serious problem that we'll have to face, especially after the change in the way we work and we live due to the COVID crisis, which is a security problem. So without further ado, just to give you context, right? So I graduated in 1971. And so when I graduated, that's what the status of the electronic industry, in particular integrated circuit industry. So we were able to put together about 3,500 transistors to verify the chip. We had a test set, a bench where wires were all over the place. The mask preparation was done essentially by hand, and the memory were actually ferroelectric materials, and we were interacting with the computer with punch card. So this is like prehistoric times, and it's only about 40 years, but it really looks like 200 years ago. Now, we then observed a very quick evolution. And so from the handcraft design that was the previous chip that I show you, you see that slowly but securely, the design became more complex. So you have Intel 404, then the Intel 8086, the Intel 8286. And you see that the size of the chip is growing, the number of components is growing exponentially, but also there is some degree of regularity that is occurring in the layout of the chip itself. Now, if you can see here on the chip on the left, there are a lot of parts of this chip that look like a bowl of spaghetti thrown on the floor. And that is indication of handcrafted design. So I would say about half of the chip was designed in a very artisanal way. And there is an evolution, of course, but while the complexity is going up towards more of a science. Now, I would like also to bring up the point that there is a theory in philosophy, which is called corsi and ricorsi, because the philosopher was an Italian, it's Giambattista Vico, that says that all human history repeats itself. And so there is always a circular motion through the ages. And it turns out that I observed this behavior in several engineering fields. And EDA is not so different from the rest. And in fact, what we see is a movement from the age of the gods, as he represented the ancient times, where senses are the dominant feature that people follow, to an age where there is the age of the heroes, where imagination, creativity, new endeavors are started. And then finally, the age of the man, where reason takes over and the behavior of humans is dominated by thinking and caution. Now, what he observed is that this comes back again. It turns around and around and around. And you can imagine that after we have an age where people are more cautious, more conservative, and so on, then there is a big crisis that brings us back to the point where the reason is not there, and we are all working out of sense. Now, I don't want to make parallel to what is happening today in the world, but you can see that some of this, it's actually true. Now, if we look at the evolution of EDA, the very beginning of EDA, so the use of computers to design chips and boards and other electronic components dates back at around 1964. And the first period, I would say, goes from 64 to 78. And what were the kind of technologies that were developed in that time? Well, one is circuit simulation. So even today, we use circuit simulation to great extent, but the roots are way back. Logic simulation and testing, timing simulation. And then in terms of layout of the components, we were talking about wire routing, PCB layout systems, and the beginning of the use of regular layouts for control logic, especially in IBM and AT&T Bell Labs. Now, it started actually, if we want really to put a beginning of time for EDA, at IBM in 1960 with the Brannin work on simulation. And then after that, there were key contributions, Brayton, Acton, and colleagues on the numerical analysis aspect of circuit simulation. And this yielded to two tools, and especially SPICE, that has been a workhorse for more than 40 years. Still today, people use SPICE that replaced completely, if you like, all the rapid prototyping and breadboarding that was so common before the advent of computers to design chips. Now, so happens that SPICE was developed at Berkeley, and in particular by Peterson and Rohrer. And when I joined Berkeley, my first project in EDA, because I was coming from a different field, by the way, was to give a hand at the development of a numerical algorithm in SPICE. And so that's the reason why in some of the version of SPICE, you see my name as a contributor, is because that was my role, to develop algorithms. Now, in terms of logic simulation and testing, there were all IBM, was dominated by IBM, with some work in university, but the most important algorithm for testing and structured testing were coming from IBM. And in terms of timing simulation was Bell Labs. So in 1975, there was the first attempt at speeding the simulation algorithms that were in SPICE by taking a completely different approach that would not guarantee the same accuracy as SPICE, but would be also much faster. And still today, some of the tools that you buy from Synopsys or Cadence, they're called fast SPICE, if you like, that has its roots in this work. And in terms of a layout, we have maze routers, we have the Hightower work, still Bell Labs, and then some at the university, Hashimoto and Stevens, with channel routing. So if you read some of the papers on EDA, the early days, these were the most relevant things of all. And the layout systems were essentially Bell Labs and IBM. Now, moving right along, from the business point of view, we realized, people realized that CAD was a strategic value for system industry. At that time, it was not called EDA, electronic design automation, but was called computer-aided design. And it was indeed a strategic value for IBM and Bell Labs and other system companies. For example, the Japanese company that were investing a lot of money in hiring people that will do this. And so internal CAD groups were the real shaker and movers. In 69, 70, 72, there was the first generation of CAD vendors. And so these vendors go by the name of Applicon, Calma, Computer Vision. But actually what they were selling were computers, small computers, very expensive, with software on top of it. But the sale was hardware, and software was on top of the hardware sale. Now, many of you may have never heard of these three companies because they all disappeared, actually. They went all away. And in fact, the first generation CAD companies, they all disappeared, so like dinosaurs. And it was very difficult to stay abreast of technology due to what? Software complexity. The software became more and more difficult to write. And the hardware evolution that was making the hardware that this company were selling obsolete really fast. There was also very little customer loyalty. So people who were buying Calma, Applicon, computer vision systems did not think that this system would be of strategic value because there was a low-level technology embedded in it. It was just a graphic editing. And then there was, last but not least, the incapacity to read the market and the evolution of new technology and the impact that this would have on their business. Now, let's then jump to 1983. It's the Intel 386 came about. Now, this was the first fundamental step towards present-day microprocessor. It had 275,000 transistors. And so the complexity problems that were embedded into the design of the 386 excited companies to push for universities to start doing work in that domain. And so, in particular, we at Berkeley decided to invest heavily in developing algorithms and tools for electronic design automation, for helping people to design things. So what you see on the right, actually you would be amazed, but the guy on the right is me many, many years ago, 1983. And you can see that I still wear the bow tie as then. And you have two of the head of the project that led to the design of the 386 and the chief architect, Pat Gelsinger. Now, why am I showing this? Because it is a basic point of my conversation with you is about the interaction between industry on one side and academia on the other side. So it turns out that Intel came to my office and said, look, we need your tools. And I said, well, our university tools, we didn't even finish developing the layout tools and the logic synthesis tools. So why do you want to use them? And they say, because we know that without some more advanced EDA work, we will never be able to bring the 386 to market. So we need you. And then we agreed. They were supporting our research at Berkeley. They sent 6 or 7 researchers, actually from Israel, first time that they use Israel as a design center. And I would go to Intel once a week to follow the evolution of the design of the 386. So it was a very tight collaboration among us. And so we bring to the, this was the middle of the age of the heroes, in the sense that there was a great interest from industry. There was a great animation in the domain of universities, and many new ideas came about. So in particular, there were key results in all areas of EDA: verification and testing, layout and database, physical verification, logic synthesis, hardware design, languages, hardware accelerators, and so on. There were also some things that you may not see today, and they were actually expert system and neural networks. So you think about AI is a new thing and machine learning, not at all. I mean, neural networks started way back. The first incarnation of neural network were actually in the 60s. And in the 80s, there was a great excitement about developing neural network for modeling phenomena that you didn't know how to cope with. So there were approximations of physical model that you didn't have the time or the insight to develop. Now, question mark, because all this attempt actually died out. So there were even 2 or 3 companies that developed expert system for synthesis as well as design, and they failed. They failed in 5 to 10 years. They all went away. By the way, the largest vendor of today were founded exactly between 78 and 92. In particular, Cadence was founded in 83 and Synopsys in 87. Now, the only oddball was Mentor, that was actually founded like Daisy and Valid Logic Systems before Cadence and Synopsys. They're still alive and well, even though they have been acquired by Siemens. So in principle, they're not alive any longer as a separate entity, because they have been bought by a large system company. Now, what made us beat the complexity of designing a chip that was 1 order of magnitude bigger than anything that was done until then? Something that is still today very modern. It is about abstraction, regularity, libraries, and tools. Now, if you look at the layout of the 386, you see, I mean, it's like a piece of art to me. You see that everything is well ordered, everything lines up in rows and columns, and there is a great sense of order, of quality. And that was the key insight that we got. In order to be able to use tools, you have to have a methodology. You have to constrain your designer to follow a particular set of rules. And so here is the story. So we use abstractions. So in particular, if you look at logic gates, that is an abstraction of a set of transistors. So this set of transistors are represented with Boolean logic. And so that is an abstraction. So you take a mathematical object that was described in ordinary differential equation, like physical objects in the chip, and you take an abstracted view and you reduce that ordinary differential equation to a set of Boolean equations. And that was key in order to be able to design microprocessors, is to work at the logic abstraction level. The other thing is that this abstraction allowed us to use tools, because abstractions simplify the problem so much that we can take a mathematical view to be able to solve the problem. The combination of abstraction and tools is actually methodologies. So the way in which you look at the problem and solve it. Now, it's my view that methodologies are actually freedom from choice. You may say, oh, it's a typo. You want to say freedom of choice. Not at all. I want to insist that the methodology is constraining the freedom of designer to use particular construct, particular abstraction, particular regularity, so that you can use tools. And so that's a key insight, that it is not so much important the tools, but is important the methodology. So that's the first thing that you have to do. So at that time, after we demonstrated that this thing worked on the 386, it was time to offload the ball. So from university off to funding companies. So in 1983, together with Richard Newton and a person from industry was Jim Solomon, we founded SDA, Solomon Design Automation, that was a precursor of Cadence. Now, you may say, okay, now EDA is all about algorithm and tool. Well, yes and no. There was also an insight about what the platform, computing platform of the future would have been. So we bet on the fact that designers would do their work on workstations. So Unix workstation and later on Microsoft PCs, but basically Unix workstation. And because of the openness of the Unix workstation, we had to think about opening the database, so opening the basic foundational of the data representation to the world. And in fact, this view was the foundation of SDA. Now, did it happen actually this way? Actually, no. I mean, it took very many years. It took up to about, I would say, 2000 for Cadence to open up the database. It was called Open Access, and still called Open Access. And there is an Open Access Foundation that gives this basic foundation to everybody who wants to develop tools and wants to insert existing work on the basis of vendors developed tools. Now, we also follow a new funding model. At that time, most of the companies were funded by VC, venture capital firms. But the reason why we formed Cadence, actually, it was because there were several companies outside. They wanted us to form a company because they didn't want to depend on universities. They trusted a company better. And so companies like National, Harris, General Electric, and Ericsson gave $1 million each. And at that time, $1 million was a lot of money, together with VC money that was only $1 million to form the company. So it was a rough few years. We almost end up going out of business, but then we had success. We had the strike partnership with the top IC companies in the world. And so we were supposed to go public in 1987. Which day? The famous Black Friday day. So the day in which the stock market in the United States had the steepest drop recorded since its inception. So we had to withdraw the IPO, and but we had everything done to go public. So we figured out that the way to go public was to reverse merge with a public company that was called ECAD. And so in 1988, we merged with ECAD and Cadence was formed. Now, Synopsys actually was founded 1 year before Cadence became a public company in 1987. And again, Richard Newton and myself got together together with RDGeos, and we formed this company. This was based on automatic synthesis. Cadence did not offer automatic synthesis at all because in 1983, the tools were not mature enough to build a company on it. Now, in Synopsys, in the old days, that was the only product that they would offer, automatic synthesis. So we had same funding model. So with VC in companies, guess what? The 2 of the 4 that funded Cadence also helped funding Synopsys. Now, it so happens that Synopsys went very well. So after the first year, we were already profitable. And so we went public in an IPO in 1991. It was a very successful going public. Now, this is an important topic to discuss, especially if we have an audience that is some people from industry, but also people from university. And this is always a debate in universities, especially in countries like Europe, actually in regions like Europe, where science is considered to be a pure thing. So no connection whatsoever with industry. But I think that this is not actually the case. So this is this debate that goes on between the abstractions and the implementation. And so you see here is a painting, one of my favorite painting by Raffaello, where you see Plato that points up to the sky, and Aristotle, which is more with his feet on the ground, that points to the earth and to say, we need to look at what happens, not only to the ideal world. We have to see how we are relevant. And so that is a continuous tension between the desire to understand what we are doing and the need to bring this thing to bear, especially for an engineering school, which brings to a very insightful diagram that I got several years ago by reading a paper by David Stokes, which is called the Pasteur's Quadrant. And this is an attempt of classifying research in along two basic axes. One is quest for fundamental understanding. So pure science, if you like, pure basic research. And Niels Bohr was an epitome of this kind of research. So Niels Bohr couldn't care less about what his physics was going to be used for. On the other side, you have a pure applied research. Thomas Alva Edison invented the light bulb and a few other things, but he didn't care about why it worked. It just worked. So don't ask why. I have this idea, it worked. Don't bother asking why it's working. And then we come to what I believe is the model that, especially in the United States, the top universities in the United States are following, which is so-called user-inspired basic research. So there is the attempt to understand why things work the way they work, but also attention towards an implementation. So why do we need to bring this thing to have an impact on the world? And of course, there is a quadrant that doesn't have any face, but I bet that you can place your favorite enemy there, in which you don't care at all about fundamental understanding, nor do you care about the use of what you do. And unfortunately, there are many people I know that belong to that quadrant. Now, there is another thing that I want to stress is when I came to the United States, 75, actually there was a lot of interest in teaching students practice. So how to make things work. And so design practice. And so what I see is like a construction that was based on putting together something and with the hope that it would stand the time. So this one is a construction in 2010. Now we are 2020, and you can see that it's not really very solid construction. Now, what I believe that we should be doing instead is to build on principles. So design science. So I want to build on principle, not techniques. So what you see here is actually a temple that was built in 420 before Christ. And this picture has been taken in 2020. Now, this building has stood up for 2,500 years. I mean, it's incredible, right? And this because it was built with science in it. So the ancient Greek knew how to build things that last. And so that is what I believe we should be doing. Now, so happens that EDA is an idea field where this consideration should be brought. Because we can do general principles, because EDA is based on algorithms, and algorithms are based on mathematics, and mathematics is a principal discipline. And so the general principles that we were able to distill from EDA is verification and design. So verification is when you have designed something and you want to figure out if what you have done is actually doing what it's supposed to do. Now, how do we manage the complexity of verifying a very large system? Abstraction, we said this before, is a very important topic in EDA and in design in general. So you aggregate objects and you eliminate unnecessary details. And decomposition. So the decomposition process is that you have a big chunk and then you cut it down into smaller parts. And this is the basic principle that my ancestors, the Romans, used to rule the world, is divide impera. So you divide up and then you master the division because each of the pieces is less complex than the whole. Now, in terms of the design complexity, well, the ways, remember design methodology, freedom from choice, you construct something that is actually satisfying properties that you are interested your system to have. And there are two basic processes, and one is refinement, where you start at high-level description of what you want to achieve, and you go down towards the implementation, and the principle of composition. You have a bunch of objects that you have designed before, and you want to compose them in such a way that you get a more complex system by composition, so that you don't need to redesign the entire thing at once. So these are the, in my view, are the two basic processes and the four basic principles. Now, you may notice that abstraction and refinement are actually the opposite of each other. So abstraction is going up and refinement is going down, but along the same axis. That is what I call vertical principles. And then you have the decomposition and composition that are horizontal. So you combine or break pieces at the same level of abstraction. And so you have these basic fundamental rules that you keep on using over and over and over again. And this is a distillation of what we learned when we started doing EDA. And so, in fact, this view of composition, decomposition, and so on enables system companies to design chips. Like, for example, we know that Apple, Microsoft, Amazon, Google are designing today their own chip. And so the way in which they can do that is because they leverage designs that have been done by somebody else. So you know, for example, that in any Apple system, there are pieces that are actually ARM cores. And these ARM cores are acquired by a third party, which is in fact the ARM company at SoftBank, and now is going to be sold to NVIDIA. But you don't have to design that core. You can import it and plug it into your design. And so the crux of the matter is how we make sure that each of the components satisfy properties, and then that the composition is actually correct, that when we put together things, they work. Now, remember, all of us have played Lego when we were young kids. And Lego, the great idea about the Lego blocks were the pins that you had on the face of the blocks that would allow the construction to be done. So the interfaces between pieces. And so the key to design by composition are the interfaces. So what you see here is actually the reverse engineering or the monster chip of Apple, the Apple A11, which has 4.3 billion transistors. So remember that we started with 1,000 transistors, maybe, and now we are at 4.3 billion transistors. How can you do that? You can do it just because you're applying discipline. And this discipline is about using the principles that I brought up before. Now, in particular, when you put things together, the first thing that you may ask yourself is that, are these components going to work together? Is plug and play, or better said, plug and pray? So let's offer the best when I compose the various blocks. So in order to be able to conquer that question, right, that problem, It says, can we say if the components, when they're put together, they actually perform the task that you wanted to perform? First thing you have to do is formalization. I love art. It so happens that when I was in high school, I did classic studies, so I'm fond of ancient art. And what you see here is Piero della Francesca, is my favorite painter. But you can notice that in these paintings, there is something very intriguing. There is this sense of calm, quiet, perfect construction. And this comes from the principle that Piero della Francesca used to form these paintings. And actually, you can see, for example, on the left of the Madonna, you see that there is a round shape on top of the head of the Madonna, which is exactly partitioning the painting in two halves. And so the entire painting, and you see the perspective is absolutely beautiful. And all of this was designed with science in mind. Mathematics was behind this beautiful art. So formalization. And actually, Michelangelo used virtual design and refinement as well. So what you see here is a Sistine Chapel. And you see a piece of a Sistine Chapel to at the right of this slide. And you see the study that Michelangelo did on this sketch that you have up, and then the actual implementation that comes down. Now, if you look at this relationship, you see that this process was actually a refinement process. He had in mind what he wanted to do, and then he obtained what he wanted to do with a very rigorous process. But it's not over yet. We were saying that we were going to use assembly of parts. And again, Michelangelo, here is Rome, the Campidoglio. And so you see, for example, the two statues on the left, they are Castor and Pollux. They actually, Michelangelo designed the square that you can see on the right from the sky view, but he didn't do the two statues. The two statues actually were Greek statues that he found in an excavation. But the two statues were not actually this way. They were reversed, and they were one piece. And so the two horses were side by side. But what he decided is that he was going to cut this, so decomposition, and then to reassemble them in reverse order, because he felt that this would give a different feeling to the entire square. So he was reusing something that was done centuries before. Same story about the bronze that you see on the bottom. That is Marcus Aurelius, and it's actually a Roman age. And he placed it exactly in the middle of a square. So if you look at this picture, it's right here. It's right at this center. And not only, but you see the design of the pavement of the square. Now this one is exactly the same design that he did in St. Peter's. So again, design, reuse. Now, the business challenges that we are facing now in EDA. So we must change continually to changing business conditions and structures. The client-vendor relationship are changing by the day, and the customers change. So our previous customers were Intel and all the big semiconductor companies. But now you have all of a sudden system companies like Microsoft, like Apple, like Amazon. And so you have to change the way in which you interact with these companies, because the interest is completely different. The point of view is different. The tools must be different because they must comply to the need of this different set of companies. But it's not enough, because the number of companies that are working in electronics is going down. And so your customers are decreasing in numbers. And so how do you prosper and you keep on growing and growing and growing? You must extend the principle to other domains and other fields. And so we come to cyber and bio-cyber-physical systems, which are important extensions of the, that could be an important extension of the methodologies that we put together for electronic systems. And so it will be pretty surprised about the kind of system that we could attack by using the same principle. So there is a basic trend worldwide which is putting intelligence into systems of any kind, of any sort. So avionics, you have airplanes that are intelligent systems. You have water distribution systems that become intelligent. You have buildings that become intelligent. Power generation distribution, smart grids, for example, are becoming intelligent. Factory automation, Industry 4.0 is all over the place, but also healthcare. So meaning that the ingress of new technologies is very important for the development. Often prevents you to think about the direct connection between the brain and the outside world through commands, through thoughts. Instead of typing, you just think about some actuation that you want to occur in the outside world. It's scary because you can imagine that you open the door to hacking and other things, but in principle, it can be done. It is already being done. Now, the other impact that we see is the fact that we can miniaturize so many components that we are going to have what has been called by many people Internet of Things. So it's not really Internet because it's not using IP, TCP, IP to connect devices, but it gives the idea of this wide network of components. Now, it is being estimated that by 2025, we're going to have 7 trillion devices. We think that we're going to be 7 billion if no pandemics occur, a new pandemic occurs, so which implies that 1,000 devices are available for every person. So, which implies that we are not going to wear 1,000 electronic devices, but they are available to us. And this will simplify tremendously the interface between ourselves and the outside world. And we see already example of this thinking. Now, so this much is still electronics. But now let's think about the way in which you build a very mundane mechanical system, which is a car. So now it turns out that there is an idea of using to design cars exactly the same principle that we are using to design chips. This was only introduction of about, I would say 10 years ago, the concept of a platform. And so you build a car by assembling modules, but cars, not the electronic part of the car itself. Now, the interesting thing about this approach is that this assembly kits that has been put together by Volkswagen, that is applied across all the models of Volkswagen as a methodology. The library may differ from car to car, but the methodology of the basic component of the library of pieces that you assemble is the same. And so actually what you see is that this modular toolkit is such that the unit cost per car is going down by 20%. The non-recurring engineering cost is going down 20%. The engineer hours per vehicle has been down by 30%. And you have a significant weight and emission reduction, which allowed the design of a new model of the car to go down from 5 years to 1 year or less. And so this was key to put Volkswagen as the company that was selling more cars in the world. So to overtake General Motors and Toyota was this very concept. Now, you know about the scandal about the diesel situation, but that has nothing to do with this methodology. This was key methodology to bring the cost down and the quality up. And this is another view of this idea of using the methodology of componing pre-existing devices, using also a continuous modification of the actual architecture of the car by allowing some part to extend, to grow in the horizontal dimension in such a way that you can use the same parts to build a small car or a big car. So the variable parts are used to adapt to different market needs, but the rest is absolutely the same. There's uniformity all over the place. Now, we talk about cars, but one place where people didn't even think that could be done is buildings. So, well, about 3 or 4 years ago, I was approached by a Australian development company. It's called Lend-Lease, which is a very large development company. They won the development of a Google campus in Mountain View. They are redeveloping the area that was the Olympic game area in London, and they are redeveloping a part of Milan, and is the ex area that was devoted to the World Expo a few years ago. Now, in Milan, they have to build something like 1 million square meters. 1 million square meters is a huge amount of land to develop. And so if you were to go with business as usual in making the buildings for this environment, it would take forever. And so the idea there is like, can we import the methodology and the way of thinking that we have used in electronics in the construction and operation business? And the answer, I hope to demonstrate, is yes. And in fact, there was a creation of a division of Lend-Lease, which is called Lend-Lease Digital, that has among its goals and missions to build such a methodology to reduce drastically the cost of construction. So all of a sudden, we find ourselves that we're concentrated on electronics, integrated circuit, and we find that the same way of thinking, it extends to cars, it extends to building, it extends to cyber system, a biological system, is amazing. I mean, and this is what I think is the future of research for the people who are interested in design and design methodology and tools in academia, and also in companies that are interested in bringing tools to market. Now, the interesting thing about all of this, guys, is that we have to ask, how safe is our design today? Can we claim, again, that what we have put together with this methodology is actually working, is that famous plug and play? What have we to do besides using the principle that I showed you before? Well, it's verification, right? And so, in fact, I'm helping Cadence to develop what is called multi-physics expansion strategy, which goes from the solution of IC design problem to the solution of designing complex systems like cars and buildings and so on. Now, what this will bring you is that if you want to verify that your complex object is actually satisfying properties, you have to develop a design platform that encompasses many different physical domains, from electrical, electronic, to mechanical, to structural, and so on, to fluidodynamics, to thermal analysis. And so you need to bring together different domain of models. So the system analysis point is that in order to be able to analyze correctly this system, you have to find solvers. You have to develop solvers. And solvers, what kind of solvers are they? It's computational software. And all that matters in order to be able to expand this way of thinking and so on, which are principles, but then you have to build the tools that incorporate this principle, is the underlying math. So you have to develop a mathematical approach that allows us to decompose and assemble and all of that. Now, the key thing to look at other domains besides the electrical domain, like, for example, the mechanical domain, the civil engineering domain, is the solution of partial differential equation. And most of the methods that are used to solve partial differential equation are based on finite element methods. And finite element methods are very large, yield very large system of equations. And so solvers are related to the fast solution of very large matrices. And indeed, remember decomposition. How do we do decomposition to solve the analysis problem? Yes, we can do that. So we want to solve a very large system of linear equation by solving smaller systems and then putting them together and finding out what is the way to compose them in such a way that I recover the solution on the entire system. And so happens that there is a way of doing that, and it is to rearrange the matrix in such a way that you have blocks along the main diagonal, and you have the borders that represent the interconnection between the various parts. Now, so happens that the method for solving this kind of solution is actually an old method that one of my advisors and myself developed in 1976. That was called a two-levels algorithm for theory. And now, what is the message here? That this algorithm that was developed way past and is based on mathematics that was pre-existing came to fruition to have a use only today in 2020. So this method was used only now for solving the sparse system of equations that are referred to the solution of the finite element method. So to the people who are interested in the theoretical job, never give up. Sooner or later, somebody is going to find out a use for what you have done many, many years ago. Now we come towards the end of my talk, and we are talking about yet another level of abstraction. So one level of abstraction above, so actually a level of complexity above what we've been talking until now, is the fact that we're building systems that are autonomous, that are capable of handling themselves alone. Now, this one is a huge market. We know that everybody plus his brother in the automotive domain is investing millions and millions in the development of autonomous technology. And we can see the actual development of this technology from 7 miles that driven by top-performing driverless car in the 2004 DARPA Grand Challenge to 10 million miles driven by Google's autonomous cars. So we see that in a very few years, almost 16, 17 years, we went from 7 miles to 10 million miles. And so there is a fast moving forward of this technology. And I also want to underline the role of government and of research financing. DARPA is the best thing that happened to research in the United States, because DARPA has a view, something that changes the way in which things are normally done. So it's a revolutionary approach. And by the way, all the work in EDA that we have done in Berkeley was funded by the so-called VLSI program, that was directed by DARPA. And so the money came from DARPA to us for almost 15 years, 20 years, that allowed us to develop that. Internet was developed by DARPA again. At that time, it was called ARPANET, right? It was called the Internet at its origin. So this money is well intended to force research to accelerate its output. And so that was the case for autonomous drive. Now, I like to stress that when you are thinking about autonomy in a vehicle, there are 4 fundamental questions that you need to ask. The first one is, where are you? So where am I? So the car has to ask itself, where am I? And so this is doesn't involve much unknown technology. It's sensing technology. So GPS, inertial, so are all technology that we know how to master, but they are essential to build autonomy in a car. The second question is, what is around me, to build awareness of the car, of its surroundings. And so you need quote-unquote vision systems, so systems that are capable of detecting what is around the car itself. And this brings to radars, lidars, camera systems. And you use machine learning for image recognition, because it's not enough to sense your surrounding, to quote-unquote see things, to have eyes. But if you don't have a brain, you don't realize your situation awareness is minimal. Now, the third question is, what will happen next? So you have to predict if a pedestrian is going to cross the street or not, if the car is going to invade your lane, if the car is going to be swerving, and what is the maneuver that you need to do. So you have to predict. So this one, in general, you need dynamical system to figure out what the movement of the object in your field of view are. And then finally, what should I do? Which is a decision system. So given the fact that I predict what will happen, that I know what is around me, and that I know where I am, I have to say what I'm going to do. And so here again, the machine learning role is fundamental. So connected cars, trip planning, and all of this is about decision systems. Now, the basic technology here is sensor fusion. So you have to fuse all these sensors, you know, GPS, inertia, radar, lidars, camera system, and what have you, together with machine learning. And so that is the challenge in this domain. And machine learning, left on its own devices, is not going to work correctly. And let me explain this in the next topic, which is EDA and AI, myth and reality. So what is a myth and what is real? So we said before that enabling technology of the future, and many people say, is machine learning and artificial intelligence. So let's look at what it is. Why people think about that? Well, the reason is very clear. It's because we are generating so much data every day that we don't know what to do with it, right? So in general, when we look at the way a human operates, it receives sensory inputs, our eyes, our ears, our touch, sense of touch, the taste of things, the smell, and we integrate all this input to send to our brain so that we can take action. But if I give you 1.820 terabyte of data, how the heck are you going to digest this amount of data? There's no way that you can master this kind of information. So we are under a tremendous mass of information that we don't know how to use. So we have to make sense out of all this information. But this is just for cell phones and mobile. But if we look, we have the Internet of Things, so the sensor, the interconnected sensor. And we look at it, by 2020, we have about 50 billion of devices already implanted in a variety of devices. You see that the generation of data is even more than what I showed you before. And so the more electronics we put into things, the more intelligent we put into things, the more we need to have a way of making sense of the data. Big data is the main driver. We have a massive amount of data. Did we have this amount of data in the 1970s when machine learning and neural network were proposed? No. Now, this method that we're trying to figure out what data need a tremendous processing power. Did we have that tremendous processing power in the 1970s? No. And so the machine learning of that time overpromised and under-delivered to yield what is called the winter of AI. So a period in which, if you in 1990s, if you went around and you say, I want to work in artificial intelligence, people will look at you with disdain, so go away. But the fact that we have all this data, so we need, and they have the means to analyze the data, brings to a new age of artificial intelligence, or I would say better, of the use of inference algorithms for analyzing data. So now, because of the richness of the data that I can collect, but especially because of a large amount of computation that I can do, then I can build systems that can beat humans. So impressive, a computer world champion of chess, 1997, and they didn't use any machine learning at all. They just used combinatorial analysis. But AlphaGo used neural network and artificial intelligence machine learning to beat the world champion of Go. And Go is a much more complex game in terms of the number of operations that you can perform and the strategic value of your operation, much more complex than chess, amazingly enough. But these are problems where the rules are well known in advance. There is no variability in the rules. What is a legal move in a chessboard is given. What is a regular move in Go is given. And this gives you the bound of a search space. But when you think about autonomous driving, can you restrict the space where humans take their decision on what to do with the car? Not at all. So in my view, the real revolution in terms of autonomous driving is going to come when all cars are autonomous. If you mix humans with cars, it's going to be almost impossible unless you make sure that humans are contain their behavior, freedom from choice. So give them bounds that they cannot overcome. And so, in fact, you see, machine learning, this is a friend and a colleague of mine, is Michael Jordan, who is considered to be #1 in machine learning worldwide. And he's a statistician. And he says, look, you know, the fact that there is all this brouhaha about machine learning makes more damage than good. And in particular, the fact of saying that machine learning neural networks are actually mimicking the way in which human brain works is a joke. It's not that way. And so, in fact, if you look at the way in which you can fool the algorithm based on machine learning, you see this simple example here that was actually done at Stanford in 2014. And you see these shapes that are very odd, but this shape up left is called, I mean, the machine learning algorithm say was a king penguin. And now on the very far left is the real king penguin, and you see very different. Then you have a starfish. I mean, beats me how the heck a machine learning algorithm can mistake this with starfish. And the one on the bottom is the African gray, which is a parrot. And please find a similarity between these two. But yet, if you train your AI in a particular way, it will make these mistakes. But why? Because the machine learning algorithms are nothing more than statistical inference models. So what you do is essentially trying to make sense out of a vast amount of data and try to find causation between inputs and outputs. But the only thing that I can verify is actually correlation. And so if I've seen something and then I decide on something else, that's okay, because I've seen it. So I've seen that this particular pattern yields this particular outputs, or something that is close to it. If there is something that is totally out of the blue, I challenge any system to be able to, based on neural network, to find a solution to that problem, because it's intrinsically incapable of global generalization. So it can do some degree of generalization on similar things, but basically different things are very difficult to find. So in fact, there is a lot of concerns about AI biases, for example. But why? Because the biases are intrinsic in the way in which you train the inference engine, right? So if I show you engineers that are only men to a neural network, it will conclude that all engineers are male. Now, we know that that is not true. It's not, and it's becoming less and less true as we move. But if I give other population where there are women as well, and you say these are engineers, the bias may disappear. But if you give only example of that kind, then the inference engine cannot but figure out the explanation for that kind of data that you've fed it. And so the need of understanding what the model actually does is real, because then you can debug this model to understand where they fail. Now, unfortunately, this model has billions of parameters, and so it's extremely difficult to figure out what actually these algorithms do. So last thing that I want to talk about, and I will be very brief, so I will skip slide and the like, because I kept you for more than an hour with me, and so it's time for you to do something more useful than listening to me. It is a security problem. Now, why is a security problem a serious problem? Because the more we depend on distributed computing, on smart work, that is all based on communication and interaction over the network, the more we expose ourselves and our infrastructure to the attack of enemies. So in particular, I want to alert you to something that is closer to EDA than other fields, which is the security of SCADA systems. SCADA systems are essentially the control components that you have in power distribution, in water distribution, in fuel distribution, everything that is our infrastructure. Smart grid. Now, the point is that all these systems are very, very, very open. So people, when they design it, and very, very old, when they design it, they didn't think about security, because nobody would have thought that hackers and enemies will attack a country by disabling their basic services, like hospital network and so on. And we know that this has already been done. Ukraine, United Kingdom, an hospital has been taken down and with great damage. Some of the hydropower plants in the United States have been taken over. So it is a real serious problem. Now, just to give you an example, in 1 year, we went from 50,000 domains that were trying to flood the network in the attempt of incapacitating the network itself. It doubled. And so we are witnessing an exponential growth in just the domain names that hackers use to attack the network. The other very scary thought is that the actual enterprise attack surface is growing by the day. And so the key weakness actually is remote access employees. Because as always, if you have a very complex electronic system and you defend it, even if you defend it perfectly, but if you have a user that has a weak password system, and you don't control it, or you don't make sure that this password system is robust, and if we make sure that this user is not opening emails or other things from their controller of the SCADA system, and by doing so, bringing in viruses, Trojan horses, and the like, we cannot guarantee any system to be secure. So unfortunately, as in the case of autonomous driving, humans are the weak link. And so we have to find a way of constraining freedom from choice, the humans, and making sure that they don't make mistakes or errors, serious errors. But the problem, besides the macro problem, as we said before, and the macro problems are the one that we mentioned, the users, the infrastructure, and so on. Only 2 years ago, there have been weaknesses being exposed at the microprocessor design level, at the hardware level. So people could enter at that low level and take over a system by entering into the electronics part of it. And these are Meltdown and Spectre, the two variations of these attacks on the basic architecture of microcomputers. And then we have to ask ourselves, why did it take so long to discover these weaknesses? Because it's very complicated to find out. And this is a diagram that I'm not going to explain for the sake of brevity, in which the meltdown attack could take place by exploiting a particular way in which the execution of a microprocessor takes place by using pipeline and virtual memories. So what to do? Well, what to do is to bring together industry and academia once more and try to build tools that will allow us to design systems that are intrinsically robust against attacks. But someone will always find a way of breaking the system, but it will take longer time, much more effort, and if we are clever at designing components of our system that can detect an attack, we'll go a long way towards the solution of this problem. So now I would like to give you a final words of wisdom, so concluding remarks of my presentation, and in particular, I want to express a thought about innovation systems. So innovation is actually as a truffle. Now, you cannot design a system to be innovative. If I look at what happened in the 386 and so on, you know, what we were doing at Berkeley was essentially truffle. If the Intel heads had not come to Berkeley to say, please help us out, we know that you have something that we can use, EDA would not have been born the way it has been born. So the dog in this case was the Intel, and the truffle were the research that we did. And another word of wisdom is that the role of academia cannot be overemphasized, actually. And if you look at the peaks of patents, H-index, if you like, of reference patents, you see that there are peaks around innovation systems, and all these peaks are around the presence of a major, at least a major university, if not more, and big companies as well. So innovation is essential for our life after the pandemics. Innovation has its root in research. Collaboration between industry and academia is essential. So don't think that technology transfer is from university to companies in one-way direction. Not at all. It's the interaction between industry and academia that makes the spark occur. There are plenty of serious problems to face, and so there is plenty of work to be done by researchers in this domain. And computational software is an important lever to solve problems of this scale, but also beware of fads. Don't think that, you know, a neural network model will solve all the problems. It's not so. You have to understand what the limitations are of this technology. So, in conclusion, it has been a long and wonderful journey for me, more than 40 years. It's not over. Much needs to be done. Hallelujah. Principle must guide our research and teaching, not techniques, it's principles. And we need new paradigms beyond what we know. And so embedded system, molecular electronics, synthetic biology, buildings, and so on. And so thank you very much for your attention. So that's all, folks. So that's the end of my presentation. I would be very, very pleased if you ask any question whatsoever. I'm here to stay as long as you have questions for me. Thank you for your attention.
Thank you very much, Professor Alberto. Excellent talk as always. So I have here some questions for you. So first one from Professor Leandro Indrusiak from York University in England. So his question is divided in two parts. First one, EDA developed ideas such as hardware software co-design and platform-based design to cope with the complexity of SOC and PSOCs. Do you think we could apply divide and conquer to the complexity of autonomous and intelligent systems?
The answer is yes, absolutely yes. And in fact, we are doing something along these lines in the sense that even the partition of the four basic problems, right? Where am I, what is around me, what is going to happen next, and what I need to decide is in some sense the application of the same principle that I was talking about. And so I believe that that is a very right field to introduce this principle. And actually, thank God, you know, people are looking at these approaches to be able to solve some of these problems. In fact, there is an interest in developing tools for designing autonomous systems. and so which is a square on the domain of EDA. And so I think that methodologies and tools are going to be very relevant for autonomous systems as well.
So another question by Professor Altamiro Suzin here from our university at Porto Alegre. So he's thanking very much for your nice presentation. And he's saying that it's a pleasure to attend your talk, having that he used your papers to do lectures in at the beginning of the Heroes era. At that time, did you believe in the so-called silicon compiler?
No, never, ever. And in fact, I remember we had very serious discussions with the followers of Carver Mead. Not so much Carver Mead because he had the right approach. But you see, the key problem about silicon compilers was that optimization was not well understood. And so silicon compilation was more than anything a translation from one layer to the next. And so you could design a chip by using computer languages and compiling these computer languages into chips. But then if you had to do a complex chip, it would be a chip that would be 1 meter by 1 meter. So it's not very reproducible, right? And so the key insight that we had at Berkeley and that yielded the formation of Cadence and Synopsys was that we needed to have optimization. So, and optimization was a key point in all what we did.
So another question by Augusto Neusling. So he's in USA now. So he thanks you again for this presentation, for all the contribution of your work for the development of the EDA. And he's asking from experience of who helped to build the present EDA, what is your forecast for the future of both EDA and IC design in general? Do you think the increasing of machine learning use will be responsible for reducing the number of engineers involved in IC design, or do you believe that tasks and challenges will be just replaced by different ones?
Different ones, definitely. So first of all, the IC design has moved definitely towards this composition of parts and this divided impedance, so this division of tasks. So if you look at the monster chip that Apple designed, you can see the structure of a chip itself, and each group was responsible for a piece of that. And so you conquer complexity by dividing the complexity in this way. Now, do I believe that machine learning is going to replace designer? Not in the least. Not in the least. Because again, you can use inference up to a point. But but if you are looking at things like, for example, the next generation routing algorithms, what I observe is that general or generic techniques to solve these kind of problems could be applied, and they yield reasonable results. But in the long term, a focused approach for that problem is always going to win if you find the right angle to solve it. For example, in the 80s, so when we did the 386, the placement algorithm that Intel used for the 386 was Timberwolf, that we developed at Berkeley, that was based on simulated annealing. Now, simulated annealing is a very interesting statistical optimization algorithm with some proven properties, but is a generic technology. So we were able to customize it somewhat by picking up the cooling schedule and by using the right moves and all that. But the moment in which the abstraction of the layout problem yielded a convex function to optimize, then forget about simulated annealing, and the problem can be solved by quadratic optimization. And so quadratic optimization is what we use today. And quadratic optimization with that particular shape was very focused on the problem of layout. And so I expect that there's always going to be a tension between general techniques and specialized techniques. And so in my opinion, machine learning is a general technique. And so for some cases, you may be able to find a nice use of it, but not for the entire EDA domain or the design domain for that matters. So it can give ideas, it can say, have you look at this, have you look at that? And the designer has to say, yes, no, maybe, let me try. But replacing a designer with a machine learning algorithm, in my opinion, doesn't make too much sense. Now, what is going to be the future of IC design, again, is this specialization of group of people being able to cope with specific issues. For example, analog design is something that has resisted a lot to EDA. So maybe in analog design, there is some space for machine learning, because right now I see people use very much experience. And so experience is previous data, if you like. And so it may be the case that an inference engine may help here, but I'm not 100% sure this is going to be. Now, is the number of IC designers going up or down? That remains to be seen, because the IC designer of yesterday were all in the IC companies, Broadcom, Intel, Qualcomm, and so on. And now there are many IC designers that are in the system companies. So there has been a growing number of IC designers that are not in the traditional IC companies. And so the number of IC designers may actually go up, but not in the standard IC industry.
Okay, thank you. Another question by Professor Altamiro Suzin. Do you think AI will continue to be a digital silicon-based technology, or we will have new technology for that?
Well, I think that silicon is seeing so much investment. It is really almost impossible to think of any other technology that has as broad a basis as we've seen for silicon. For certain specific components, then we may go to different technology for sure. But silicon is going to be the base no matter what. And because of the entire ecosystem that is based on silicon. Now, if you ask me, is the Moore's law going to stay? It's going to stay for a little while, but then at some point, it will run out of steam. And so how are we going to cope with that? Well, with architectures, right? So we are going to find new computing architectures, new composition of sensor actuators, new packaging techniques, like, for example, 3D IC. I noticed that you have a talk that is going to talk about 3D design, and that's definitely a trend. The other one is what I call what everybody calls chiplet-based design, in which you can put together naked chip, not packaged chip, on a substrate. Is what was called a few years ago multi-chip modules, right? But the chiplet approach is going to be quite dominant in the future. So it's going to change the IC design towards these new architectures. But I don't see silicon to be replaced by any other material in large scale, always large scale that I'm talking about.
Thank you. A question by Clovis Figgenbaum. Why do you think that we weren't yet able to replicate with technology the way humans learn from example as a child and experience? Because obviously machine learning and AI isn't doing that well. Would it be because we yet don't understand completely how the human brain works in terms of learning?
Well, definitely yes. I mean, if we were able to understand how our brain works, and we would have solved. There was a Francis Bacon. I studied philosophy for too many years. So Francis Bacon was a philosopher in the old times, right? And we're talking about Queen Elizabeth time. And Francis Bacon said that if we could find the way, we could understand the way in which the brain works, we would have at that time was very much search whether a man could actually bear a child. So it would be a man bearing a child, meaning a very difficult thing, almost impossible, or by now we think it is impossible. But that was a goal of understanding how the brain works, how we learn since the medieval time. And now we are in 2020, we still don't know how our brain works. And that was the insight that Michael Jordan wanted to give, is that, look, what we do with neural network and the like is a cartoon of how the brain works. And I have friends that are actually medical doctors, also because we have a new research trying to use inference techniques to detect if we are facing a new pandemic, right? That's a serious problem. That you cannot use algorithms because you don't know what is going to happen. So you have to use inference. There is no other way. But these doctors tell me that the brain not only has these neurons that are on the surface, but there is yet an unknown way for the reptilian brain to coordinate the work of the brain. And so they claim that the role of the reptilian brain is still to be discovered. And they conjecture that the reptilian brain has a lot to do with our capabilities of invention, of finding something completely new, which is based on the fusion of a lot of information. But if you look at the way a little kid learns, it's really mind-boggling, and definitely is not of the same structure of an inference engine or the training of an inference engine, not in the least.
Thank you. Now, talk by Professor Mario Casu from Politecnico di Torino. So it seems to me that AI ML systems, as they've been designed so far, miss the notions of abstraction and compositionality.
Right. Absolutely yes. Absolutely yes. Because if you look at neural networks and the like, we look at them as flat, right? And then we train a flat neural network. We don't find components there. So we don't abstract away the behavior of islands of neural network, for example. And because we don't understand how neural networks actually perform their task, because there are so many parameters, we have no idea how a particular information is processed to come up with an answer. And that's the point of explainable AI. So how do I make sure that I can explain what I do? And indeed, decomposition and abstraction, in my view, is the only way to be able to do understandable AI.
So a question by Eduardo De Conto. So regarding security, what kind of tools and algorithms would help in your view? Do you see AI and ML as a future technology, or could it just be a gloried statistical inference method? Would it fail as an initial times of EDA?
Yeah, okay, very good question. So let me first look at the security, right? What kind of tools and algorithms? So for one thing, is there are certain weaknesses in the system that we build that could be prevented. If you look at the way in which hackers enter into our system, they exploit bugs, right? So they exploit errors in our coding that will expose part of the software system to be invaded by an external entity. So the first thing to do would be to follow a synthesis approach, right? So if you look at chips today, I claim that most of the control algorithms that are implemented are actually correct. Why? Because by now, the synthesis algorithms have been proven for so many years, and they are based on theorem and proof, right? That are foolproof. So it's very difficult that you can break into a logically synthesized part of a chip. But software, my God, you have tons of errors that can open doors to external people. So if we were to find a optimized compiler that would identify mistakes, and we have to develop methodologies so that these mistakes will not appear, as we did in the case of electronic design, then I could compile software that would be error-free, and that will go a long way to prevent attacks. Now, of course, I can be as good as I can on this part, but if I have users that access the system with passwords, then I'm always going to be, how to say, prone to be attacked. And now, what would be a tool to prevent that? In my opinion, there is nothing else but biometrics of some kind. So a combination of iris detection, face detection, fingerprint detection, voice detection, but a fusion of all of this would make the access to computing systems so much more robust than we have today, because we will not have to rely upon something that is being chosen. It's something that is mine, and I've been born that way, and there's no way in which I can change it. So I think that biometrics is going to be a very important step towards entering into system in a more secure way. And then last but not least is the verification aspect, or actually I should say better, the monitoring aspect. So in fact, I've been working with two companies. One has been acquired by Intel, another one has been acquired by Siemens, that had as their goal to place observers on the chip that could detect motions of information at the chip level. And so it's beyond, it's bare metal security, as we call it. It's beyond the software. It's down at the nitty-gritty detail. And if I see something that is not expected, then I can raise a red flag and say something is wrong here. Now, that may be because there is the system is broken, or because someone is attacking the system. But I have a way of using this observer, both for safety and security. And that is yet another important tool, is observation, observing what is occurring inside the chip and placing circuitry inside that are capable to see the motion of information to the register level.
Thank you. So
and also, yeah, glorified, yeah, the other question was about glorified statistical inference method. Yeah. It's my opinion that that is what it is, right? So it's glorified statistical inference. And why is it a separate field? Because given the fact that we have all this computing power, then we can develop sophisticated techniques to improve these statistical inference methods. Improve by adjusting this, adjusting that, correcting this error, correcting that error, being able to demonstrate that my test set is rich enough. All of this can be done today to improve the basic working of the statistical inference method, but that's what they are. And so we cannot go out of it. And so in the old times, when we use neural network and the like in the 70s and 80s, the computing was not there. And so expert systems, same story. Expert systems, not neural network, there's nothing to do. And the old expert systems, they were based on, they were rule-based. So based on experience and based on what people used to do, and then you try to figure out what rules people have followed, and you apply these rules in sequence to go from point A to point B. Now, this has failed miserably, and so the algorithms that we're able to develop outperform these approaches. Also because we were able to limit the space of a design. So, for example, when we do design at the register transfer level, we work with synchronous systems, right? So we have finite state machines and the like. And this goes a long way to eliminate a lot of problems. And so if we could do the same thing in software or in the system design and safe system design, then we could indeed eliminate many of the attacks and do not only in terms of security, but also the quality of design would be so much better.
Okay, thank you. So Eduardo do Conto also ask about suggestions to improve contributions between industry and university.
Yeah, well, that's a very interesting question. Now, I have an entire talk about this. Maybe I can give you another talk, but I've observed it, and I have a very rich collaboration with the industry. Now, say this, I publish a volume of papers and so on. So the key point is that you have to realize that when you interact with the industry, you are not trying to do the work that the industry does, nor industry should do your work. So the first thing to understand and to respect is the roles that each industry and academia have, right? So in addition, you have to be able to have is what I call the receptors. The receptors are people that are inside the industry that are interested in discussing the principle, in understanding what you're trying to do, and then being able to take that, to receive that, and turn it into something relevant for the company itself. There are some things that are easier to do than others. For example, tools are much easier to to interact with industry because you have a proof of existence by running the tool and showing what this tool can do. There are other research that is much more difficult to demonstrate to an industry that it actually works. And so you have to have someone who's willing to put his career on the line to say that what you're doing is actually correct on one side. On the other side, though, you have to prevent this view, remember Plato, with the finger up and Aristotle with the hand up. But a Platonic approach will never work. So the point is, if you have industry that comes in and say, I have this problem. So Intel came, I have this problem. So if you say, well, I'm interested in statistical optimization algorithm, like simulator annealing, and finding the convergence property of this, and don't give a damn about your problem. You read my papers and then you figure it out yourself. We would not have generated EDA at all. So the point was, let me understand what is your problem. And let me see how I can take what I know how to do and adapt it in such a way that can be relevant for you. And that is my role as well. So to work with industry. Remember, one day a week, I was going to Intel and with my hands on the chip and figure out where the tools had a problem, where the tools were working well, and say, oh, I understand. Quest for fundamental understanding. So then I change the algorithm because I understand what was the problem. And so this is very enriching. But if the industry is asking you, come with your students and do this thing, which is a menial task, it's just they consider you as a cheap labor, that is never going to work. Is demeaning, is the wrong way for industry to interact with academia. On the other side, as we said before, if academia say, I don't care about industry, we do a dirty job, I don't want to get involved, it's the opposite sin. So go away, I don't want to hear from you. So the sin of industry say, well, you are, cheap labor. And the sin of academia say you are the devil, you don't want to recognize our work. So it is always interaction between entities is based on the interaction between individuals. And so there must be mutual respect. You must find the right person on the other side that is going to interact with you.
Thank you. Question by Rafael da Silva. So first, he's stating that it's excellent lecture. In your opinion, with the evolution of machine learning and all the embedded technology being used in autonomous, semi-autonomous vehicles, would there be a deadline for the end of traditional cars?
Well, yes. I mean, I think that traditional cars are already dead in some sense, right? Because if you look at most of the cars right now I'm not talking about, you know, your basic model, but middle of the and up, right, and the top level cars, they all have so many sensors and the like that is not like autonomous driving, but you know, you can do a lot without getting you involved. Think about, you know, there are lane departure module, so that if you kind of wavering around and you're going over the lane boundary, it will alert you. If you're falling asleep, it will see your eyes and will tell you wake up, right? So I would think that this one is already a lot of assisted driving that is taking place. Assisted parking is there. You have all these cameras and bing, 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 bam, bam, bam. Can tell you don't go here because you're too close and all that. And now there are companies that sell you automatic parking software, right? So it depends. If you want to call this still a traditional car, you may, but I don't think it's a traditional car where everything was done manually. Now, if you think about the, you know, in automatic shift, there are two kinds of automatic shift. One is a traditional one that has been around since, you know, the 50s, and one which is the so-called robotized gear shift, in which the gear shifting is occurring like in normal hand shift cars, but it is done with an algorithm, a microprocessor, a control algorithm, and a complicated mechanical infrastructure, right? So that is a robotized thing, and so that is indeed a step towards having an automated, a different kind of cars. And this was, you know, I had the luck of participating to the initial development of this technology because it was in Formula One, and it was 1988 when I went to my first, you know, Grand Prix of Formula One, because they were trying to introduce this robotized gear shift, and in particular was Ferrari. And I remember very well the pain that I had in terms of the noise, the tremendous noise that you have in Formula One, and the success of that approach in making Ferrari being more effective in the behavior of a car. So I think that the evolution of automobiles has gone a long way towards automation. So it depends where we draw the line between a traditional car and non-traditional car. Now, of course, the movement to electrical is going to make everything faster because an electrical engine is so much infinitely simpler to control and to manage that everything that has automation is going to be terribly simpler than in a traditional car, except the decision making, right? Like, for example, do I brake, do I accelerate, and that kind of stuff, which is nothing to do with the fact that your engine is electric or your engine is fuel driven. So that's different consideration. But I think that we already left the domain of traditional car. Now, if you think about fully autonomous cars, then it will take a while before we get there. But remember, my view, the only way in which we are going to get there is to limit the behavior of people. So prevent people from doing things that are crazy, right? So, and I've seen all kinds of things. I mean, I've been driving for what? For 60 years now. No, well, let's say 55 years. And I've seen everything known to man of crazy behavior of other people. And I went very close to have accidents because of other people's behavior, I think. So that is the main limitation. Still humans. I mean, get the humans out of the way, you know, and let the cars drive by themselves. It would be much fewer accidents. Actually, probably no accidents, no deadly accidents. It will be a wonderful world. But we have to deal with what the world is and not what our best idea of the world is going to be. So here we are.
As you talked about Formula One, just a comment. I learned a few days ago that the engine of all cars have a control using a chip designed in Brazil.
Oh, how nice. That's
yes.
Fantastic.
So we have a question by Professor Rafael Brum. He's saying that we are honored to have you here at CASS Talks. Thank you for this wonderful lecture. And his question is, debugging algorithm designed to tackle NP hard problems is challenge enough? The buggability of machine learning based algorithms thought seems to be obscure, to say the least. How do we cope with that?
Yeah, well, very good question. Now, is interesting because when I came to the conclusion that most of the most of the useful algorithm that we had to develop for design were actually trying to solve NP hard problems. But the key issue was to use what I call meta heuristics. So way of simplifying the search space or to analyze the search space that would allow us to solve NP-hard problems in very short time. So my recommendation for this particular NP-hard problems, the point of view was, who cares, it's NP-complete or NP-hard. Let's try to solve it anyhow. And by now it's even more important because we have so much computing power. So right now, nobody is scared anymore about NP-hard problems. So people go and try to solve it, which is good. Now, when we talk about debuggability of machine learning-based algorithms, the point is that a well-posed question? In my opinion, it's not. Because, again, the number of parameters that you have and the fact that there is no structure except the layering of the network that can help you trying to figure out what the actual engine or algorithm or model or synonym here do. It is impossible because there are billions of parameters. So forget that. So unless we decompose the problem and unless we overimpose a structure. So once more, my idea of freedom from choice. So don't make the neural network completely general. Restrict the neural network to have a particular architecture that I understand. And so it's still a glorified inference model, but I have a way of understanding what this statistical model is actually doing. And so that's my only way to say how we are going to cope with the debuggability problem, or what they say is actually explainability. So how do I explain that what these algorithms do?
There is still 3 questions. This is okay for you?
Oh, sure. As I said, I'm here for as long as you want.
So next one is, again, Eduardo de Conto. I heard some interesting ideas of brain-inspired computing with things like memristors. Any option on this subject? Could it impact the design paradigm?
I don't think so. I mean, we are a million miles away. By the way, memristors are nothing like a particular relationship between flux and charge. And so it was postulated by Leon Chua which called memory storage, was an element that didn't exist in life, right? Because we had capacitors that have a direct relationship between voltages and charges, a resistor, direct relation between voltage and currents, and inductor with a direct relation between flux and current. So the missing element, like in the Pasteur quadrant, was flux and charge. And so if you postulate the existence of this, then you open up a different way of storing and not manipulating, but certainly storing information. That was what memory stores do. Now, do I call this brain-inspired computing? Not in the least, because the brain doesn't work according to the relationship between, flux and charges. But the way in which the human brain works is all at the architectural level. So we have a huge amount of components, which are the neurons. But we know that these neurons are not doing every piece of our brain is carrying out a particular task. And so a brain mapping problem is to try to find out which part of our brain is actually controlling our speech, which part of the brain is controlling our movements and all that. And we know a great deal of that. We also know that there is some degree of interchangeability between parts, so that if we have a stroke and a part of our brain is incapacitated, and so we cannot speak well any longer, there is another piece of our brain that takes over. But it's never the same, so we cannot replicate exactly the other one. So we know that there is plasticity, so that things can change in the structure of the brain, but we know that there is structure. There is structure. And so when we talk about brain-inspired computing, what we need to find out is what this structure of the brain is. And we need to understand what the heck is the reptilian brain doing, what the heck is the cervelletto is doing, what the heck is the deep cortex doing, and so on and so forth. And the mapping of the areas of the cortex that do things for us. But then there is a big issue of feelings, right? And feelings are very hard to find out. So where is the center of love, for example, of rage? We know that there is some relationship between certain areas, but we don't know which ones. It's too complex. There are many areas that come together, but there is a structure there. And so until we find this structure, we are not capable of doing anything that will be even remotely brain-inspired.
Okay, thank you very much. So now a question by Arto Oinonen from Tampere University in Finland. Which area of EDA have you personally enjoyed most? The increase in abstraction is inevitable, but has it made engineers happier?
Yes. Okay. So what did I, well, I must say I love them all, right? Because I always try to find something interesting or unsolved that then I was able to at least to try to solve. And since it went well on a number of occasions, so I enjoyed that. There's nothing better than being able to do something and then seeing that it actually works. So that is the key point of saying, did you enjoy? For example, if you play tennis and you know that you played a game well, then you are very satisfied, right? If you play tennis and you miss all the shots, you get very frustrated, right? And so that's similar to that. So if you try to solve a problem, a layout problem, you cannot do that, then you get very frustrated. So I think that the key point is to be able to find an angle that will allow you to understand what the structure of the problem is, and then finding a way of solving it. This is the most enjoyable thing. Now, probably the thing that has given me more pride is not so much EDA, but is this platform-based design that someone has referred to, and that I didn't have the time to talk here, but is an idea that came when I started working with BMW Magneti Marelli and Mercedes, because I found that this is a principle that I applied without knowing it, and that I applied to EDA, and I found out that this was a key to expand some of the EDA thinking in the other fields. And so that really gives me, right now, the thing that I like the most is this expansion to buildings.
Thank you. Question by Tulio Bittencourt.
Yeah.
Some airplanes already limit what pilots can actually do. Do you think 100% autonomous vehicles will start by airplanes or cars?
A very good question. I think airplanes. And why airplanes? Because it is there are professionals that drive airplanes, right? So there will always be someone sitting there, but he will not drive. Is capable of driving in the case the system fails, because I don't know a lightning came from the sky and has hit the electronics. Then what? Right? So there must be someone who's able to take over if the system fails. But as you pointed out very correctly, so pilots can do some things, but not everything. If you look at the some of the latest big airplane accident came from the fact that the pilot did the opposite of what he was supposed to do, but either he wasn't trained, talking about training, was not trained well. So the last 6, 7 issues, right? 7, 8, 7 issues were that. So 3 planes went down because the pilot didn't know what to do. And so it was a change in the architecture of the plane that made the autonomous system to work in a different way than expected. And so the airplane went down. The other one is the American Airlines plane that took off from New York, and the pilot that was his first or second experience actually got scared because the plane was leveling and going down a bit, but that autonomously so because it needed to gain speed, right? So we see that sometimes when we take off, there is and then we go and again, this is normal maneuver. But he got scared, said, "Oh my God, the system is not working." And so he was fighting the system until the plane went in vertical stall like this, because the autonomous system and the pilot were fighting one against the other. And so that is something that, again, the human in the loop, we have to be extremely careful about what we allow people to do. And so that freedom from choice is extremely important. Now, why do I believe airplanes? First, because as I said, the drivers, the people who are operating the plane are professional, while cars, everybody can drive a car. And second, there are many more degrees of freedom that you can exploit to avoid problems, because we are in the air, so there is not a single place where we can go at a certain level of altitude. Well, if we are in a car, I cannot slam against the wall. There are physical constraints that I cannot leverage. But if I am a plane, I can do maneuvers like moving away, moving down, and moving up. And so you have so many more degrees of freedom. So that is, I think, one reason why, 2 reasons why the airplane is going to be the first fully autonomous, even though it's already such. I mean, if we really look at it, and if you are flying over the ocean, it's completely autonomous. The pilots go around, talk to the people, and so on. I mean, just the plane flies by itself. It can land by itself, by the way. Sometimes it's done that way, especially when there is a difficult weather condition. You let the plane land, you let the system land the plane, not the human. So I think we are ready for this stage. Right.
Thank you. It appears another question by Rodrigo Verdick, here from the Federal University of Rio Grande do Sul. about the academia and industry interaction. Due to the amounts of industry secrets, it is quite hard for the students to find the right path for the leading edge technology specs and techniques. I mean, those things are not usually in books and so on. What you do advise for undergrads who are seeking a trail inside the vast world of microelectronics to overcome this problem?
You don't, essentially, no, seriously speaking. You know, there are ways in which you can be exposed. For example, if you intern into a company and you sign NDAs and the like, and you are limited as to what you can look at and take off, then you have an interesting view on what is going on inside the company. And so many of my students have done internship at Intel, IBM, and so on. So they know what they need to know. And when we were working together on some of the technologies, now the embodiment of the technology into software code was kept secret, but the algorithms were all coming from us. So we were allowed to publish. And I remember at some point in time at Berkeley, we had two rooms. One that were completely segregated with security. Security, one was IBM security, and the other one was Intel security. And they even had the physical access being manned in different ways. Why? Because in one room at Intel, we had all the actually information of the 386. So you can imagine if someone would take hold of the full design of the 386 would be a total disaster. But we had it. Why? Because they needed us to try to solve their problem and using their design as a test case for our algorithm. And for IBM is that there was at the time when the AIX machine, the workstation, IBM workstation, was being disclosed. And so they had the machine, and nobody knew that they had such a machine. But they wanted us to play with the machine. And so that's the reason why the room was absolutely locked with all kind of dark windows and everything to prevent people from looking inside, from outside. Even the color of the machine was a dark secret. But the interest of the companies was high enough that they allowed us to keep these two things on our premises. But you have to be trusted and you have to have signed things, right? But the signing things is not enough. You have to be trusted. And my students who had access to these two rooms were actually graduate students, not undergraduate students. And their thesis was about developing this methodology, and they were very happy to be able to test their methods on a real, difficult, extremely complex system. So that's it.
Okay, thank you very much. Maybe I can do final questions.
Yes.
What do you think about the number of transistors that are being used in most of chip nowadays? Do you think that there is still a large opportunity to optimize the amount of transistors in a chip to reduce power consumption?
I mean, it's not so much as, again, it's an architectural question. It's not the number of transistors that make a difference, but it's the architecture of a transistor that makes a difference. So yeah, I'm sure that all of you know about the dark silicon. The dark silicon is part of the silicon that doesn't consume power. Why? Because it's little used. And so the question is, can we eliminate the dark silicon or not? Or it's okay to have dark silicon on the chip? Is it a waste or is it okay? In my opinion, we are capable of putting so much stuff in the chip that I don't particularly care about the fact that some of the chip is not used all the time. Because when it is used, it may be crucial. It may be the difference between me and my competitor. So that's okay. And I was very surprised that the actual optimization of power does not really come from logic design and the like, but it comes from the technology. For example, if you use bipolar versus CMOS, right? That's obvious, right? That CMOS consumes so much less power than bipolar. And if you are capable of having like, for example, these trench isolated things and so on, and you limit the leakage current and so on, you reduce the amount of power that you consume by a large amount, much more than you can do by designing the gates or the blocks in your. On the other hand, the other part where you gain a huge amount is at the top of a design, is where you design the architecture. So the top and the bottom are what matters, not the number of transistors, it's the architecture and what technology you're using. These are the ones that have the largest impact on the behavior of your chip from power point of view.
Okay, so thank you very much, Alberto. We could still talk.
My pleasure.
We have a large debate, but I think it's time to finish now. Thank you very much for this excellent talk, and also to be available to this large set of questions. Probably we had today the record in the number of questions, and and today we had by the people that announced herself in the chat of YouTube, we had today an audience attendees from Belgium, USA, Italy, France, UK, Peru, Portugal, Finland, Greece, United Arab Emirates, Switzerland, and many locations in Brazil. So thank you very much again. Thank you also to all that listen to this excellent talk by Alberto. Thank you very much again to spend your time with us today. And I hope to see you in person in the near future.
Yeah, indeed, because by the way, as a closing argument, I was supposed to come to Brazil to this kind of conference that you organized so many times. And every time there was something that prevented me from coming. So at least I didn't have any excuse, but so I was very glad to participate in this conversation. But of course, I would love to be in Brazil. I love Brazil. So
it will be a pleasure for us if you can visit us in near future.
Absolutely,
also.
Absolutely. Okay. Thank you very much.
Thank you very much.
A glass of cachaça together. Okay. Good night.
Thank you. Bye bye.
Bye bye. Bye.